Hi everyone, as we move into chapter 3, we're going to continue talking about alkanes and hydrocarbons, but in the context of its three-dimensional shape and conformation. So here we're going to be focusing on the conformation of both straight chain alkanes and also rings in the second portion of the chapter. So we've talked about molecules in 3 dimension, and in a previous chapter, we discussed how we know that methane, CH4, is a tetrahedral. And we know that it's this shape because it is the shape that maximizes the distance between electron pairs. And the distance between these angles we also talked about is 109.5. Remember, I told you to remember these bond angles, in particular the one for the tetrahedron. So generally, in drawing a tetrahedron, and in methane in particular, we use a drawing style that's customary of showing this three-dimensionality. So I'm going to show you that right here. Generally, it's customary to show the hydrogens of the methane with two full lines that depict hydrogens that are in the plane of the paper. So just a regular line like this and like this. And then with a carbon-hydrogen bond that points out of the page, we draw this using a wedge shape. It's usually depicted like this. That means it's pointing towards me out of the page. And then with the other carbon-hydrogen bond pointing into the page, we use a dashed drawing. So again, this is kind of the artistic rendition of a methane, but shown to kind of represent its three-dimensionality. It's the best you can do with the 2 dimensions showing its 3 dimensions. And again, this is to show the tetrahedron where each of the angles here are 109.5. Okay, so here's a nice representation of that, and you can see I've added a GIF here to show you what that rotation looks like and how we can represent it in 3 dimensions using our 2-dimensional drawing trick. So here you can see, again, all of the carbon-hydrogen attachments with the bold wedged line showing the carbon-hydrogen bond pointing out. You can see it in this GIF here that when this is forward here, and you look at the drawing, it has the wedged there, right? Okay, and then when it's rotated backwards, we can see that that is now imagined as a dashed line. So this is the same molecule, we're just rotating it, and we're showing how we can represent that rotation using a 2-dimensional drawing. And again, these are equivalent molecules. They're the same thing, it's just rotated. But let's look at something a little bit more complex. So here is ethane. Now, when you talk about ethane, we know that both carbons on ethane remain in a tetrahedron. That means that the hydrogens around that carbon are all 109.5 away from each other, and also the respective carbon next to it is also 109.5. So we can draw this in 2 different ways, however. You can take the same structure, and as you can see again in the GIF, we're just rotating it over 180 degrees. And when you look at it this way, you see in this depiction, the 2 hydrogens are pointing up. That's this picture right now in the GIF. And then when it's rotated around, the two hydrogens are now pointing towards the top like this. These two are in the same plane with each other. So again, we can just rotate this whole molecule. We're not moving any bonds, we're just rotating the whole molecule. And again, you can see different three-dimensional depictions, but of the same molecule, right? It's just the same molecule moved around. And a reminder, if you can superimpose a molecule on itself, if you can rotate it and superimpose a molecule on itself, that means it is the same molecule. Now, what we're going to be talking about today is actually the rotation around the carbon-carbon bond, around this bond that can happen in all of our alkanes, our straight chain alkanes. So the two CH3s are joined by a carbon-carbon sigma bond, remember, single bond, and rotation can occur along this bond without disrupting connection. So we can freely rotate one of the carbons around, and I'm going to show you an example of this in the next slide, without breaking any bond. And by doing this, by letting this carbon rotate around, it gives rise to a variety of three-dimensional shapes, right? Because we can have different positions in which the carbons are opposite of each other, where the hydrogens are in different positions. These different shapes we call conformations or conformational isomers. Sometimes they're also called rotational isomers. Meaning, again, this is the same molecule. So it is not a constitutional isomer in which you have actually changed the positioning of a bond, right? No bonds are being moved around. We are just rotating the same molecule. So it's a special type of isomer in that it really is just the same molecule, but it can be in different conformations. So here again is a depiction of that with our ethane. You can see this is the same molecule, it's just ethane, but we're showing rotation and how these hydrogens can rotate around a carbon in one position. And I want to remind you, this is very key. This type of rotation can occur on all single bonds like this. So in the future, when we're thinking about where things are, always remember that around a single sigma bond, these carbons always have free rotation. And we will talk about circumstances in which free rotation, in which that rotation gets blocked, which gets locked in. But otherwise, remember that this free rotation is always occurring. Okay, so here again, like I said, is a GIF showing the movement around that bond. So you can see these are the two different conformational isomers that were shown on the previous page. One where two of the hydrogens are lined up at the top, and then you rotate it as shown, and you can see they're kind of staggered now. And again, the difference is subtle, but they can be interconverted just by rotating that carbon-carbon bond. This is a 60 degrees rotation. You can imagine that you could continue to rotate along this bond as much as or as little as you want. Ethane technically has an infinite number of conformations related by rotation around that carbon-carbon bond, because as I just said, you could rotate it as small of an amount as you want or as large of an amount as you want. Well, we're going to talk about important conformations, important positions of ethane in particular, and then of other molecules. And these important conformations we're going to name as staggered and eclipsed type conformations. A staggered conformation is a conformation where each carbon-hydrogen bond is bisecting a hydrogen-carbon-hydrogen angle. To put this more simply, if you look at this picture here in this staggered conformation, you can see that each hydrogen, this hydrogen here, is going between this carbon hydrogen shape here. That's what they mean by a hydrogen carbon hydrogen angle. That's this angle right here. And you can see it goes between it, or it bisects it. Similarly, this one goes between this angle. And you could do that for every single one of these hydrogens. They're all staggered in a way that there's no direct overlap of a hydrogen and a hydrogen. An eclipsed conformation is the opposite. It's where each carbon-hydrogen bond is exactly aligned with the adjacent carbon-hydrogen bond. And again, you can see that here, this hydrogen and this hydrogen are aligned with each other. These are aligned, and the ones in the back are also aligned. So everything perfectly aligned. And again, that's the staggered versus the eclipsed conformation. These are words we're going to be using. Now, ways that we can represent these molecules in 3 dimensions and kind of easily talk about the conformations are via these different methods. And I want you to be familiar with being able to interpret each of these methods. So we talked at the beginning about the wedge and dash artistic drawing of conformation. This is where you're kind of looking at the molecule from the side on, and we're using the dashes and the wedges to represent where things are coming towards us or away from us. So you can see here that this molecule being represented by a wedge and dash. Again, we're looking at the side where this hydrogen that I've highlighted is coming out at us, and that is this one here with the wedge. And this hydrogen here in the back is going away from us, going into the paper, and it is represented by a dash. Now we can also use a representation called the sawhorse representation. This one isn't used as often, but again, just be familiar with what it looks like. In this type of representation, we're going to be looking at a molecule kind of from a almost head-on angle, but just slightly at the side. And you can see in this case, we're not using wedges or dashes because we're just looking at the molecule at the side angle. And you can show where each of the molecules are positioned in this manner based on pretty much where they are positioned along the central carbon. Now, the method that we're going to be using and talking about the most throughout the rest of this chapter is the Newman projection. The Newman projection is a way to look at the 3-dimensionality of a molecule and its conformations, where it's overlapping, etc., by looking down the center of a carbon-carbon bond. So here we've actually turned the molecule. This is the same molecule, the same ethane, but we've turned it so that the 2 carbons here are completely overlapping each other. And you can see only the hydrogens in the back, or anything that's connected to that back hydrogen, just poking out from the back. But otherwise, this whole bond here between the carbon and the carbon is completely overlapped. So again, we're looking right down kind of the barrel of that bond. So always know that a Newman projection will be looking down the center of one carbon-carbon bond. In the case of ethane here, we only have 2 carbons, right? This ethane is, if we wrote it out in our bond line formation, we remember that it's just this molecule. So there's only 2 carbons. We're looking down this bond, the center of this bond. And here you can see the hydrogens on the front carbon are always represented in the front of the circle. So these hydrogens are the red hydrogens in the picture. And then the back hydrogens or the back connections will always be written on the outside of the circle. This circle here is just supposed to represent the carbon in the very front and how it blocks the carbon in the back. Okay, so again, just to kind of get familiar with the Newman projection, we're looking end on along one of the bonds. And you can see here is ethane. This is the position that we're looking, where the I is. You look along the carbon-carbon bond. Here, we're looking at an eclipse situation where the hydrogens, remember eclipse is where hydrogens are aligned with each other. And so in the eclipse conformation, this is how we would draw it. Now, don't be confused. They are slightly off center. The only reason that we draw it like this is where we draw the hydrogens just slightly apart is so that you know what is in the front and what is in the back. Technically, these are completely overlapped on each other. They're only drawn just slightly skewed, again, so you can see what is there. But this is how you draw an eclipsed conformation. So each of these hydrogens, here, 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 and here, are the ones that are directly paired with each other from front to back. Here is the other conformation we talked about, the staggered conformation. Again, when you look along the carbon-carbon bond here, you see that the front hydrogens, these are the front hydrogens, this one, and this one, kind of line up with the spaces between the back hydrogens, which are here, here, and here. These are the back hydrogens. So this is actually what we call the maximally separated version. So often when we're talking in Newman projections and talking about different conformations of molecules along these angles, we're interested in the angle between the two bonds. So for example, the angle between carbon-hydrogen bonds and ethane. This angle is what we call the torsion or dihedral angle. To show you kind of what that means is, if we're talking about looking down C and B here, we're interested in the angle that exists between this BA bond and CD bond. So this chain here is called the dihedral angle. What that looks like is when D and A are lined up, in this case, this is in an eclipsed molecule. We say that it has a dihedral angle of 0. There's no angular difference between D and A. Again, looking down the molecule using our Newman projection. However, when we put this in a staggered view, one of the staggered view, and A and D are opposite of each other, this is what it looks like in the Newman projection. You can see they look opposite of each other at an angle of 180 degrees. So here, this angle is 180 degrees. We call this anti, sometimes when they are opposite of each other. But again, we're going to be talking about these angles, so where things are in relation to each other based on their torsion angle, or what we call dihedral angle. So Newman projections, I think, are pretty simplistic for understanding these angles because you're just thinking of things in position around a circle, right? Where one rotation around a circle is a full 360 degrees. So if this is our 0 degrees starting, then something at 0 and this position are 180 degrees apart. This would be 90 degrees. And think about our positions in between as well. So some more examples of this. Again, here we're looking at ethane. Ethane with a torsion angle of 0, we call eclipsed. Certain torsion angles we give special names, and I've already been kind of using these so that you are getting familiar with them. Another type of torsion angle, 60 degrees, when we have two items, one in the back and one in the front, that are 60 degrees apart from each other, we call this a gauche position. When we have two items, again, one in the back and one in the front, and they are 180 degrees apart from each other via their torsion or dihedral angle, we call this anti. So again, these are words that we use to describe positions of two attachments, in this case it's hydrogens, along a molecule in relation to each other. So let's look at all of those dihedral angles that can exist, again, with ethane, our 2-carbon long chain with all hydrogens on it. Here, 2 of the hydrogens have just been labeled in red so that you can kind of track them better. But remember, these are all the same thing. They're all hydrogens. So we can have staggered and eclipse formations as we go around. Starting off in an eclipsed formation, you can see when these 2 hydrogens completely eclipse each other, all the other ones do as well. This is at the 0 degrees mark. It is eclipsed. When we move by 60 degrees, our dihedral angle, the hydrogens become staggered. So this is a position in which all of them are completely non-overlapping each other at a 60 degrees. If we move it another 60 degrees to 120, the hydrogens become eclipsed again. Now, the hydrogens marked in red are not eclipsed with each other, but we still have hydrogen on hydrogen eclipse happening. Again, another 60 degrees to 180, you get staggered again, where all of the hydrogens are non-overlapping. If we do another 60 degrees, 240, eclipsed, and 300 staggered. So this is with ethane. Remember, ethane does have all hydrogens on it. So it has this very patterned response where every 60 degrees it goes between being eclipsed or staggered, eclipsed, staggered. And again, you can see this on the GIF as we rotate it around. Now the changes between the molecule in its eclipse or staggered conformation actually has an energetic value. So the gauche or staggered conformation is lower in energy than the eclipsed conformation. This means that there is a small barrier to rotation, and in particular, this energy is 3 kilocalories per mole. Now, that amount is not a big enough amount to stop this molecule from rotating. It will continue to rotate in between the eclipsed and staggered positions freely. However, it does mean that generally this molecule will tend to be in the staggered conformation as opposed to the eclipsed conformation. Again, because the staggered is lower in energy, because you just have less overlap of those hydrogens on each other. So again, eclipsed conformations are the least stable, generally speaking, for almost all molecules. And staggered conformations are the most stable, conformation in which there's no overlap between molecules. And again, to remind you, this is a barrier to rotation, but it doesn't stop rotation. So these molecules will still always be rotating between these positions. It's just that they are more likely to be in the staggered position than the eclipsed position.